Hello, everyone. I'm super excited to be here today and to have the opportunity to talk a little bit about the work that we've been doing to improve JavaScript performance on React Native. Quickly, who am I and why am I here talking about this? So, as Christopher said, my name is Tadeu Zagallo. I joined Facebook in the beginning of last year, and I started working on React Native a little bit before it was open sourced, and I was doing mostly iOS, and then I started doing more performance work and focus more on tooling. And by September, when we started the new React Native Perf team, I switched to it to working full-time on it. And that's what I've been till now. Today I'm going to be talking mostly about the startup. So here's an overview of what the framework has to do when you start a React Native app. So we have to go to several steps. You don't have to memorize that, of course. It's just a quick look. So we have to load the JavaScript. Then we have to load all your native modules. And then we start the VM. And only then we inject this module metadata that tells the JavaScript what can it access in the native side. After that, we can inject your JavaScript bundle that has your application. Only then we can run the actual application that will cause React to render. And then we do the layout. And finally, we can create the native views, and you can see your app. That's just the basic of how it works, and hopefully when I come back to talk about what we've did in this process, it's going to help you understand. But what are we trying to achieve with React Native? So Bonnie talked earlier about the motto, learn once, write anywhere, and that summarized the idea that a developer should not have to learn a whole new skill set just to target a new platform. And that's basically the idea of React Native, but also we don't want to trade user experience to developer experience. The user experience shouldn't be worse because you're having a better developer experience. And the other big thing about React Native that we care about is hybrid apps. So for companies that already have a big app, like Facebook, for example, we can't just throw away not just the apps, but all the infrastructure that have been built to support these native apps. So this helps shape our performance goals. So we care about, especially, memory usage. So if we have a whole app running already, you can't just afford to use a lot of memory. We have to have a low memory overhead. And the same thing goes for startup. So if you have an app that's fully written in React Native, and it takes a couple hundred milliseconds to start up, it's okay. Like when you tap an app, you expect it to take a little bit before it opens. But when you switch from a native feature to a React Native feature, if it takes a couple hundred milliseconds, it's not going to give the user that native feeling. So in order to make it better, we've been working on some native optimizations as well. So we've done things like multi-threaded initialization. So that graph that I showed at the beginning, the first steps weren't actually true. All of this happens, but it's not all in one line. So we try to parallelize that as much as possible. So right now it looks a little bit more like that, in fact. So we try to load the script and the native modules and the VM all in parallel. And we have to wait a little bit until we have the modules in the VM, then we can inject the metadata, and then finally we can run the application. And we can go further, and if you have native modules that we're not using, before you would create all of them at startup. And that's not ideal. Once you have more than one feature written in React Native, they might use different native modules, and you would pay the price for both of them. So if we remove all the modules that we're not using, the graph looks a little bit more like that. So we don't need to wait for the module. Some modules might be initialized during this process, but we don't have to wait on it. They will be loaded on demand. We also worked on smarter batching. So when React Native came out, it was advertised that it was async and batched, and that's true. But during startup, we can't just wait too much time creating a batch and leave the other threads idle. So in fact, when React Native came out, we weren't very good at multi-threading. So I've showed this graph before. You can see at the top, there's the JavaScript execution, In the middle, you have the layout, and at the bottom, we have the native part. So creating the native views and rendering it. So these three things are happening in different threads. But if you look at the boundaries, they are not happening in parallel. So we have multiple threads, but we're not doing work in parallel, in fact. So that's not taking advantage of the multiple cores. So then we started doing layout in parallel, and things got a little bit faster. But the native part was still at the end, and wasn't being parallelized properly. So the next step was also start creating the native views in parallel with the layout. So as soon as you render something in JavaScript, we try to send that as soon as possible to native. We do the layout, and as soon as we have the layout, we create the view. But this talk is not about native optimizations. It's about JavaScript optimizations. So we also did some optimizations in the client JavaScript. So Buan talked at React.js Conf about inline or lazy requires. The idea here is that usually we have all our requires at the top of the file. And that's good, because once you open a file, you know everything it uses. But the problem with that is that once you require one file, it's going to require all of its dependencies. And therefore, so all the dependencies are actually loaded up front, no matter if we're using it or not. So what lazy requires do is that they move the requires to where they are actually used. So in this example, when you touch this button, we'll show an alert. But if you never touch it, that's never going to be loaded. Of course, this has trade-offs. If that module has never been loaded and you tap at it, it will have to execute the JavaScript at that time, and it might not be as responsive. But the trade-off has paid off, has been good for us so far. And we do some simple dead code elimination as well. So if you have some code that's wrapped in a if-dev, and these variables provided by the packager that we use, and then we can eliminate all the module that's conditional to the development environment. Also, if you have some code that's platform specific, we can use only the platform that you're actually targeting. So for instance, this code, if we're compiling for production where dev is false and we're minifying the code, we would completely strip the dev module, and we would not just remove the require, but also the module would not be included in the bundle anymore. And we would only have one require for each platform. So if we were bundling it for iOS, you would only have require alert iOS, and the same thing for Android. So those modules would also not be in the bundle. We did some more things. We optimized the polyfills we had, and that was quite important. We used like a not very fast require. We removed some of the bubble helpers and a bunch of other like smaller JavaScript optimizations. But after that, we stopped to take a look at what the distribution during startup looked like between native and JS. And it looked a little bit like that. So just to help out, everything in between these two blue arrows was JavaScript. So it's more than 80% was spent in JavaScript. So what next? Sorry. So when we come from the web, we usually think about like our JavaScript as this input that goes through this black box, that's the VM, and we get some output. So if the VM doesn't like the input, it's going to be slow to execute. And what we do, we shape our code in terms of the VM. So we know what the VM can or cannot optimize, and we try to avoid the patterns that are bad for it. And then we kind of shape our input in terms of it, and hopefully it gets faster. And that's how you have to do it. You can control what virtual machines they use using. It can be on any browser or versions of browser. You can limit where your app runs, but still, the only way to have full control of it would be to give the user your own browser to load their website. But on React Native, especially on Android, we ship the VM with the app. So we know the exact version of the VM and which VM is running. And we can actually modify the VM if we need to. And in order to do that, let's take what the VM looks like. What's the process that the VM goes through to run your JavaScript. So the basic idea is that you give the VM some source code First thing it does, it copies the source code, then it will parse it, it will generate the abstract syntax tree, and then from that it will generate the bytecode that the JSC executes its own bytecode, and then it will execute it or interpret it. But they wanted to make it faster, right? So from VM started using JIT compilers. So JS introduced a baseline JIT. So JIT is just-in-time compiler. So once you have a function that's executed multiple times, the VM will try to make it faster, and it will compile it to native code. So the baseline JIT, it's not an optimizing compiler. It will basically translate bytecode to machine code one-to-one. It adds only polymorphic inline caches on top of it, but that's a separate topic. And then they kept going. So they added a new tier of JIT. So if our code runs even more times, it will go to the next tier, that's the DFG. And DFG stands for data flow graph. So once you have the data flow graph of the program, then you can actually start optimizing it. And then it will be able to do inlining and other nice optimizations that all of the modern VMs do. And they didn't stop there. They kept going, and they added the FTL. That's the fourth tier of JIT. That's called faster than light. And it used an LLVM backend, and it does some very aggressive optimizations, but the throughput wasn't good enough. So to get there, first of all, your code would have to run hundreds of thousands of times for a single function or a loop. But still, they didn't stop there. They replaced the FTL recently, and there's a very good post about it in the WebKit blog, with the B3 backend that's called bare bones backend. That does similar optimizations to FTL, but it has better throughput. But in fact, in iOS, there's this rule that they mark memory pages as non-executable, and the only way to have writable executable memory is if your apps sign with the Apple-only dynamic signing code entitlement. But what does that mean? It means that third-party apps can't JIT on iOS. So we're back to stage one. We have no JIT. But you might be asking, this is mostly about Android for now, and what about Android? So we can JIT on iOS, on Android, pardon. And if you really like JIT compilers as I do, we're probably very happy. But it turns out that it's slower, so it's not a very good improvement. So there's a star there. So actually, we are using the baseline JIT, but we had to increase the number of times that a function has to run to try to have it not run on startup, because it would make startup slower, and this is about startup right now. And adding the other tiers, DFG and FTL, makes it even slower and increases the binary size quite a lot. So what do we do now? If just adding more and more layers of JIT is not the solution, what should we do? So we go back and we profile. And it turns out that the time that we spend on the VM during the startup looked a little bit like that. So at the bottom, you have parsing and bytecode generation, and that's about 80% of the time we're spending during startup on the VM. So yeah, it turns out that parsing is actually expensive, but I mean, there's a bunch of very smart people working in the VM, and we are not the first ones to figure it out. So again, I had simplified the initial graph a little bit, and in fact, it looks a little bit more like that. So at the top, you have two modes in the parser. So at the top, you have the AST generation mode. So that's when you actually generate the AST and the bytecode, as I talked before. And at the bottom, you have this syntax checking mode. But what does it look like in practice? So let's say we have the sample code. It's very simple. It's just a hello world in React. It's been compiled, so there's no JSX. And to represent what it looks like, I built the state of the VM is at the right, and the source code is at the left. It might be a little bit small to read in the right side, the state of the VM, but hopefully the graph will be enough to understand. So here we haven't started yet. So the AST is empty, and there's a parser cache at the bottom that's also empty. So we go to line 1, and we find a var declaration. If you have watched Jeff's talk on Flow yesterday, that might sound familiar. So the left-hand side is an identifier, hello, and the right-hand side is a string, hello world. So we put the AST there, these node there, and if we go to the next line, yeah. And we find another variable declaration. the left side is an ID, and the right side is a function. But when we find a function, we save it at the bottom. What's the offset of that function? And some metadata that's not filled in, and it's going to be the next step. So now, we actually, if you see at the top, the symbol changed, and we are now in syntax check mode. So we will not generate any AST for that. And the only thing that we do is that we find that this variable hello actually lives in the parent scope. So we have to save that in the metadata of the function. Then we step out of the function, we go back to AST generation mode. We save the next node. There's a function called left-hand side, the member expression. The right-hand side, it's just, and you have some arguments, sorry. So now React is going to call that function, but you don't have the AST for that. So what the parser does is that once it needs that function, it goes back and then it generates the AST. So the parser is lazy. For anything that's not necessary right away, so if it finds a function and it doesn't know when it's going to be executed, it will just check if the syntax is okay, and then it will go through it. And once you need it, you parse. But if we had this cache up front, we didn't need to do the syntax checking. We could just keep it right away. And we tried that, and we called it the pre-parse cache. So we tried that. That's what the graph looks like. So now the execution time shifts a little bit, and we spend more time in execution rather than in parsing and generating bytecode. But we can keep going. So when we try to execute the function, the first thing we ask is that, does it have bytecode yet? And if it's the first time, no, it doesn't. So we have to generate the AST for that. Then we generate the bytecode. And then we can cache that bytecode for the next function calls. And finally, we execute it. So if we call the same function again, now we have the bytecode, and we go straight to execution. But what if we always had the bytecode? So we could just go straight away. There's no need to generating any AST or doing any syntax check or anything at all. So we also try that. It's the bytecode cache. And now there's no parsing. There's no AST generation. There's no bytecode generation. We do spend some time on fetching that bytecode from disk, but it's minimal compared to the time we spent parsing or generating the bytecode. So this is Android only for now, and it's very experimental, so it's not available yet. But we had a more pressing issue to solve. So as I mentioned, as you start, so if you really like React Native, but you already have a native app, you might decide to write a new feature in React Native, and then you have your app with a React Native feature. And let's say everything went smooth, and you liked it, and you have a new feature to write, and you decide to write it in React Native. And it's, okay, you add a new React Native feature, and everything is going fine. So by now, you really like React Native, and you decide to write more features in React Native, and very good. But at some point, you're going to realize that all this JavaScript lives in the same file. What that means is that for every new feature that you add, you make the bundle bigger, and we still have to parse all these things at startup. So the actual effect is that every new feature makes all the other features slower, and we can't have that. We can't just prevent people from adding new features because it's going to slow down the previous features. So enter random access bundles. So the idea behind it is that you write your code just as you would, and it's going to be packaged. It's going to be compiled with Babel, and then it's going to be packaged to something like that. So you have a bunch of define calls, and the left-hand side is the method name and some factory function. Then we replace that with numeric IDs. Next step, we add this hash table at the top of the file that tells where every module starts and ends. But that's not like, it's not an actual JavaScript hash map. It's just we write the bundle in a binary format, so that's just 2 integers. So it's just 8 bytes per module. And after that, we put the global code. So the code that has to be executed upfront. And after that, we append a new byte terminator to every module. So what happens is that next time we require a module, we can just do something like that. So this is not the actual code that we use, but the idea is it should explain the idea. So when we require a module, we check if you have done it before, and if you did, we just return the cached version. If you didn't, we keep going, and we check. If we don't have the factory for it, that means that the module haven't been defined. So we just load it from disk at this time. And after that, we can just execute the function. So if you have a feature that's never required, that JavaScript's never going to be injected in the VM or not even loaded from disk. So now we solve the problem of linear slowdown based on the number of features you have. And the best thing about it is that if you've been using React Native already, and you've been using something like that to bundle your application, so once you have a React Native application, you can just bundle the JavaScript and put that in the app and ship it. You can just append these 2 letters to your command, and you have that, and you can use it, and try it out, and let us know if that's going to help. If you've been doing React Native, that might be helpful for you. And before finishing, this was a bit quick. I just wanted to thank you. Like, there's a bunch of people on the team, and I get to come here and speak. But of course, I didn't write all of it. So there's much more people on the team. David, Dan, and Michal, who are all here. So if you want to know more, come talk to us. And they worked on all these features. And that's it. Thank you.